let's wrap up this capacitor stuff with this video here. We'll try to keep this one a little shorter than the last couple, so you won't be falling asleep as fast. Stop it, Billy, wake up, wake up. Okay, good Billy, good Billy. Okay, so now we know that our potential energy, all right, our capacitor can store energy, and therefore that's potential energy. You store energy in a capacitor. You fire up one side and give it a bunch of negatives. Now you have potential energy stored. These electrons want to go from here to there. When you're not where you want to be, you have potential. What are the equations for that? Our equations for potential energy in a capacitor. Now we have a potential energy of a particle in an electric field. That is PE equals QED. All right, that comes in handy dandy notebook sometimes. But if we want to get the capacitance potential energy, we have an equation. Some orange here. That works, and it looks like this. If we do a unit analysis on that, do it. You won't. No, you won't. You come out with joules, okay? Because this is coulombs, okay? That's a coulomb. This is joules per coulomb. Coulombs cancel, joules. So that is it's going out to be joules. This is our potential energy of a capacitor equation. Now, handy dandy, and it does come in handy sometimes, we can make a substitution here for that Q, because C is equal to Q over V, and therefore Q is equal to C times V. And if I do that, I'll get C times V, which is 1/2 CV squared. That is another handy-dandy version of the potential energy of a capacitor equation. Whoa there. Where you going there, big fella? All right, now we'll take a look at our equation sheet. Yeah, look at all these equations in there. So many equations for electricity and magnetism. That's what we are here. And now we're moving our way down here. We've covered a bunch of these now in the videos. There's the one in capacitance in the last video. All right, and there's the one just above it in capacitance. And here we are right there. Right here. I just put those two on the board. Those are right there. They're right there. Okay? Well, yeah, but that doesn't say potential energy. It says U. I know. AP likes to use U as PE. PE is a U. And that's why you knew that. You knew that. It's funny. It's funny. Okay. So here are our two equations for potential energy in a capacitor. So this is going to help you out with some of the problems that you have in the assignment for the week using the potential energy equations and our capacitance equation. All right. One thing I do want to talk about, though, to wrap up this unit on capacitors. Please wrap up this unit, my God. I can't stand it anymore. Whoa. Jeez. That's kind of harsh, Isaac. Relax, okay? Relax, everybody. It's lightning. Lightning. Come on, we'll wrap it up with something fun and interesting. Lightning is fun and interesting. Do you know what the lightning capital of the world is? Lightning capital of the world. It's in the U.S. Florida. State of Florida has more lightning strikes than any other place on the planet. Okay? Florida. Yeah. Well, you're out, prancing. Oh, with Mickey. I've got this just, by the way, as my Disney shirt. Show you different animal kingdom to parks on it. Yeah. Oh, hey, let me check it out. I'll show you. There he is. There's my buddy, Figment. Imagination. Yeah, Figment, my buddy. Oh, so you're down there frolicking with Figment in Disney World. Watch out for those lightning bolts. Lightning is nature's capacitor. Yes, it is. Nature's capacitor. So let's say we got a house here, or a church. We'll make a church with a little cross on the top. Okay. Well, can you see that? That's kind of hard to see. We'll change it up for you here. Put a house. Leave my house in green. And then we got a tree. Here's a tree. There we go. Nice tree. And here's you. Okay, there you are. That's you. It is. That's you. It looks like you. It does. I can see you. Okay, so now what happens is you know this thundercloud, cumulonimbus. Cumulonimbus. Remember? Movie Up? Yeah, he knew. What was his name? That kid. Up. No, I can't remember his name. Russell. Russell, 100% muscle Russell. That's who he is. Yeah, he knows his clouds. Cumulonimbus, look out for those. Now, in a cumulonimbus, what you end up getting is there's a lot of updrafting and downdrafting, these particles smashing into each other within the cloud and causes electrons to be released, and they separate. It becomes like a big battery, basically, is what it looks like. And so in the bottom of the cloud, negatives accumulate. Now, those negatives, you know, they don't like each other. They want to go do something. They want to just kind of like just hanging out, chilling like a villain. They want to go do something, get some action. Man, let's go do something, yeah. So now what are they going to do? Well, let's say that you've got a bunch of negative particles accumulating at the bottom of this cumulonimbus. Then what ends up happening is, well, everything on the ground has a bunch of negatives in it. You have a bunch of negatives. Don't be so negative. Funny. Now you know that everything has negatives. And so these negatives are going to create a huge field of electricity here. Now these negatives are going to repel the negatives in anything down here on the ground. So there's a bunch of negatives in the tree and in the church and in you. A bunch of negatives in you. And what they do is these negatives say, I don't like you, and these negatives say, we don't like you, so you know what? We'll run away. We'll head out of here. Let's kind of move down, away. Let's get these negatives. These negatives say, ew, yucky. Move down. And these negatives in you will move down like this. And so what does that do? That dipolarizes you. That makes you a dipole. Because what happens is the top part now becomes positive, relatively speaking, as we push the electrons away from this large accumulation of positive. Like that. Now, we've given those electrons a reason. Yes, we have. Here's the thing. Dry air is a relatively good insulator. This is a capacitor, people. What have we done? We've set a capacitor. Look at it. Look at it. Look at it. Look at it. Oh! The uglies. Remember SpongeBob when he had the uglies? He thought he had the uglies as a breath. And he said, oh, look at it. Look at it. Ah! SpongeBob. So we have negatives here, positives here, and an insulator in between. That is a capacitor. So this is our dielectric here. Dry air, decent insulator. But it's been raining out with our cumulonimbus, most likely. So you can get lightning occurring when it doesn't rain. Lightning bolts on zipping back and forth there. But when it rains, that breaks down the dry air dielectric, and wet air is not as good of an insulator. So this dielectric, as it's been raining, becomes weaker and weaker. Now these electrons can go, get out of my way, you puny dielectric, I am coming through. You would not stop me. And these electrons will go, boom, they'll discharge. Okay, just like a capacitor will do. They'll discharge. And boom, one big fell, boom, nailed it. Usually, the electrons will go to the highest charged thing, shortest distance between, two things, straight line kind of a thing. And so usually it'll strike the highest thing around. Not always. The lightning kind of doesn't follow all the rules all the time, but it usually will strike the highest thing. So there we go. Now, if you happen to be that highest thing around, Restro, you're in big trouble, mister. Michelle, Full House, 1996. Check it out. So let's say that you... And of course, what happens is, in a capacitor's recharge, they discharge and they'll fill back up. If you've ever had a photographer take a picture and they got the flash unit, they can't take another picture right away because that battery's got to recharge that capacitor. Now you're ready. Same thing happens in nature. It's not going to be just one lightning strike and game over. If you have one, you're going to have more because this will recharge and boom, recharge and boom. And you just don't want to be down here at the end of the boom. Now, if you're the only thing out there, we'll redraw you here to the center. Okay, like I said, you're in big trouble, mister. Or missy, whatever you want to be. And you could be both. This is the 90s. You could be both. And let's say that that's you, and you're the only thing around. And now, your hair will start to do this. What the heck is going on there? Well, it's kind of like an electrostatic generator. Your negatives have been pushed down here away from you, leaving you with all positive, and like charges do not like each other. And so your hair will try to get as far away from possible, but at the same time be attracted to that negative cloud in the sky. Huh? Pretty cool, huh? Well, not cool if that's you. That would not be cool, okay? Boom. And then wham! Yeah, it could be game over. Probably will be. Might not be. People survive lightning strikes. But don't try this at home, for professionals only. Okay. All right, just a little lightning safety here. If you do find yourself caught out in the middle of the field when a lightning storm rolls in, which, like, why would you ever get caught like that, I suppose? I suppose maybe if you're hiking up somewhere in the middle of nowhere and you didn't expect this thunderstorm to roll through, then, okay, what do you do? What do you do? Well, you get down as low as possible. Don't lay in the ground. You don't recommend to lay in the ground, but get down the balls of your feet. I'm going to do that right now, okay? I'm getting down the balls of my feet. Oh, here I am. Hey, kids. Here I am. You get down the ball of your feet. You lessen the contact with the ground at the same time, decreasing your height. And don't stand near one freaking tree in the middle of the field, for crying out loud. That's stupid. But, however, okay, ready? If there are a clump of trees or woods nearby, or an area where there's a bunch of trees, then if you've got a bunch of trees, you're better off getting to that area than standing out in a field by yourself. All right? The odds are if you're in a field by yourself, you're it. Game over. But if you get to a bunch of trees, especially a wooded area, go in there. Well, won't the trees get struck? Most likely, yes. But you won't. Most likely the trees are going to get struck and you won't. You just wouldn't want to be leaning up against the tree that got struck, so you get in a bunch of trees and you try to keep yourself distance from the trees and hope that the lightning doesn't strike a tree near you and travel through the roots of the ground and electrocute you. It's all a game, kids. It's all a game, but we're decreasing your odds of surviving. Okay, kids, we'll wrap that up. Remember, nature's capacitor, don't mess around with it. Lightning, it don't play. It don't play.